And here is a high-priced mathematical model. You see, if you unroll this to this point, then you see that you can get the volume of the paper because you'd have a length here that would be in red, and you'd have a width this way that I have in green, and then the differential thickness would be the thickness of the paper. So your volume would be this by dx, say, whatever. And then if you wrap it back up, then it looks like this, and you can see the sense in which the shells of paper, where what I had unwrapped was one of them, all together fill the volume of paper that you have going around the roll. So a way to understand the shell method is to think of the model from the toilet paper. So this is what I have. Notice I tried even to be true to my colors. Patriotic, right? So you see you have this dimension, which would be like the green, wherever it is, and then your circumference, when you unwrap, is the paper hanging down, and then the dx would be the thickness of the paper. So you should be able, if you can write a reasonable formula for the volume of the paper, to imagine filling up your geometric figure with these shells of paper and set up a Riemann sum the way that we did, for example, with the boxes with the pyramid, and take the limit of the upper sums and the lower sums, and if they agree, then what they agree on is the integral. The same story over and over again. So dV then is the volume of a shell, so it would be 2 pi times the radius. That's your circumference. 2 pi times the radius is the length that hangs down. I think it's always a little bit surprising to me, no matter how many times I do this, how far the paper hangs down for one turn around. Circumference is, I think, surprising to people a little bit. Anyway, then the height would be the green, and the thickness would be the dx. So for problem 1, 6.2, the curve here, the upper curve, is 1 plus x squared over 4, which you notice is a parabola. You wrote y equal. And they're talking about the volume where this is the top curve and the bottom is the xy plane, say, of the figure as x goes 0 to 2. You notice that when x is 2, you have 4 over 4, which is 1, so your y is 2 as it works out. So x is going from 0 over 2, y is also going to go, well, let's see, actually y would be, when x is 0, y would go 1 to 2. So that's the Christmas cake in the morning, right? And so then 2 pi times the radius x, height 1 plus x squared over 4, thickness dx, would be your differential volume. And so, as always, what we do, disguising setting up those upper sums and lower sums and all that, is take our expression for the differential of whatever it is we're after, volume in this case, and put the integration sign on it and figure out our antiderivative if we can. And in these problems we'll be able to, and go from there. Of course, you cannot always get an antiderivative, and what you do then is the subject of one of the sections in chapter 8, which we'll get to later this spring. So we are multiplying the x by this, so that's how I get x, and then x cubed over 4, and then I take my antiderivative, and I have x squared over 2, and I have x fourth over 4 times 4. Put in my limits, and I get 6 pi, which is what the book says it is. So this seems to work very well. There is, however, a catch to this, which I'm about to explore with you. You see, in this problem, the graph is increasing as x increases. X, remember, is your radius, and as x increases away from the y-axis, the height of the shell is increasing. And so if you wanted to talk about the kind of thing we were doing yesterday with the pyramid, where we had the sum of volumes of boxes that were all too small, that we called the lower sum, and the sum of volumes of boxes that were all too big, that we called the upper sum. And then we argued that our true volume had to be squeezed between those, and since they both had the same limit, we could say that limit was the volume, and then that matched what you got with the antiderivative. If you were here, and I'm sure you were, you remember doing this. Well, reasoning in this way, which is always what's underneath doing an integral by getting the antiderivative like this, you could say that we could talk about an inner or a lower sum of shell volumes where we would take a minimum radius on any particular shell, say little r, and we could get the height at that radius, which would be the green on this edge, by putting the r into the formula for the top curve, the little r. So we could have 2 pi times this radius times this height, and that would certainly be a minimum in this picture. You can see the curve is increasing. And in the same way, we could have an outer radius for this particular shell. In other words, the other side of the sheet of paper here, and use that radius to get your height, which would be a little greater than this height. And so that would certainly be an upper sum. And you could say then that whatever is the true volume of your shell is squeezed between 2 pi small r, the height with small r, and 2 pi big R, height with big R. Okay, it seems as though it works fine, but look at problem 2. Here's a graph of problem 2. You see it's another parabola, but this one is opening down, and as the r increases, the height decreases. So you can't say in this problem, as you could in this one, that on the one side, in problem one, you took little r, and the height, that was the smallest radius, and the height at that point was the smallest height. Here, if you take the smallest radius, this kind of tan color, that's your maximum height. And if you take the bigger radius, the green, then the purple here is the height, and that's your minimum height. So then you can't say that taking this r and the height there is that the product is the maximum, you see, because it's the smallest r, and you can't say necessarily that using the bigger r is going to be a minimum just because the height is minimum there. See, so you have a difficulty. Well, actually, people from the time of Leibniz, who developed calculus in Germany, and the Bernoullis and Euler, who were Swiss, and the early workers in calculus on the one side, and Sir Isaac Newton, who developed calculus in England at the same time, and people in his school of thought, they just didn't worry about it. They assumed it was all right, because if you take a typical problem, you can probably work it with both methods, the disk method from yesterday and today's shell method. And when you do, you get the same answer. So they said, well, that has to be proof that it's all right to go ahead and do your antiderivative, even though you seem to have this logical difficulty. Well, in the last 100 years or 150 years, mathematics has become more rigorous, and so people wanted to prove that this really is all right. And the person who did this is the subject of the first handout of the morning. And he was department chair at the University of Chicago, which is, of course, a very good school. And this has a picture of him, tells a little bit about him. And on the other side of the paper, we have the theorem that we need in order to justify going ahead and writing our integral side, working problems the way that you expect to do them. Or not, but you see, if you turn to the other side of the page in my handwriting, what we're dealing with is the difficulty that you have a product of two functions. You have the product of the one function, which is your radius, and the other one, which is your height up to the curve. So you can call one of them F and one of them G, it wouldn't matter. So he showed in general that if you have two continuous functions, F and G, that if you set up your Riemann sum with where you're taking F at one point in your little interval and G at another point, not necessarily the same, that limit of the product of the functions times the length of your subinterval does give you the same integral, whether the two functions are evaluated at different points or at the same point. And this is what people had assumed must be so for about 200 years before the time that Bliss really proved it. I should say one thing, and that is that people like Gauss and Euler, did so much mathematics that they just didn't bother to write down their proof of everything they did and send it into a journal to be published. And it may well be that either or both of them had done, basically in their heads perhaps, the sort of thing that Bliss actually wrote up for publication. We don't know. I would never want to stand here and try and say what Euler did not know or what Gauss did not know, but they didn't publish it. Anyway, it is all right to work an integral like we did this one, with the product of the radius and the height to the curve without worrying about the fact that you might not want to evaluate the radius and the height at the same point in order to construct what would really be a lower sum or really be an upper sum. So that's what I've written about here. So his theorem then is that if the two functions are continuous on the interval, then the integral of the product is a limit where you might evaluate the one function at one point and the other function at a different point. Could be the same or different, and it will still work. That's what we need to know. So back to problem 2 now. Having addressed the logical objection here, we could say our volume again is 2 pi times the radius, which gives us circumference, times the height, which in the case of problem 2, the height above the x-axis is 2 minus x squared over 4, parabola opening downward. So multiply by the x, and you have 2x minus x cubed over 4. And so you have x squared minus x fourth over 16, and is 6 pi. It's just a happen so that problem 1 and problem 2 are the same volume. The shells in problems 1 and 2 were vertical, like I'm positioning the paper there, but they could be horizontal. For instance, look at problem 4 in 6.2. And what you have is a sideways opening parabola, and you have a vertical line over here at x equals 3. And you notice that when x is 0, y squared would be equal to 3, so y would run from minus root 3 up to root 3. And what the problem wants is this volume, and of course it would be down here. You know that because if you look at the picture in the book, they're showing it. I realize you don't, all of you have the book with you, but you'll see that it's clearly marked in the book. They mean this and not this. And so the thinking of your shells as thinking of your axis this way now for a problem like this, you want the length, which would be 3 minus the curve, 3 minus the curve is here, then you want your radius around the x-axis, which would be y, as I marked here in the blue, which would be this, and then the thickness of the paper would be the dy. And y would go from 0 to square root 3, second mistake of the morning, that I caught. We don't know how many I didn't catch. Okay, and so you notice the 3's cancel and the sign changes, so this is all y square, and this is y, and so you have y cubed to integrate, 0 to root 3. So this is y fourth over 4, 0 to root 3. Root 3 to the fourth power gives you 9. 2 into 4 gives you 2, so you get 9 pi over 2, which is what they say it is. So most of these problems can be done either way, either yesterday's method with the discs or today's method with the shells, and many times it doesn't make any difference really as far as how much work it is. Of course, if you're doing them correctly, they're going to give you the same answer. Sometimes the integral may be easier to do in the sense of figuring out the antiderivative one way compared to the other. But what determines the variable, x or y, is what you're using for your differential thickness of the shell, say, if you're thinking shell method, or the thickness of your discs or washers if you're using yesterday's method. So if you have something where the thickness is dy, as with the shells when the axis of rotation is horizontal, then that means everything else has to be expressed in terms of y. Because when you're doing an integral, the dx or dy or d whatever is your favorite letter, that letter names the axis on which you're doing your partition, and it's the limits of the sums on that partition that are theoretically what your integral is. So this says everything has to be in terms of y, whereas in these two, where your axis is vertical, your thickness is dx, so everything has to be in terms of x. Some of the problems will require u substitution, which you heard about in Math 170. And so look at a problem like this one. This is where our curve is 9x over square root x cubed plus 9. And we're talking about the interval on x, 0 to 3. Notice what we have with our graph if we do a little bit of table work. When x is 0, of course your y is going to be 0. When x is 3, you have 27 here, and you have 27 and 9 making 36. And then the square root of 36 is 6. So your y value is 27 over 6, which is 9 over 2, which is about 4.5. So this curve looks something like this. It goes from 0 up to 4.5 as you go 0 to 3 this way. And so we're talking about the volume that we get if we rotate around the y-axis. So we have 2 pi times our radius, and you notice the thickness then of the paper would be the dx, and we would have the x radius times our curve, our 9x, and so we have 9x squared then over the square root x cubed plus 9. So this problem is made so that U substitution will work nicely. Of course, when you're writing a book like the book you have, you have to spend a lot of time trying to design problems that people can do reasonably with the methods they've had. And so you have either the 12th or 13th edition, so this book's had many years of various people designing problems to work nicely. The original Thomas book came out of, I think, about 1953, and it revolutionized how people teach calculus in this country anyway. There are many other books like it that have come out since. But Thomas was really the first one to require the equivalent of 3 semesters to cover it and to include the solid analytic geometry and the vectors, which is Calc 3, and the various applications that are in the book and so on. So anyway, people have been working on the book and improving the problems for 60 years, more or less. So with this one, if you call this U, what's under the root sign here, the du would be the derivative, 3x squared dx, because this is always what we mean by a differential, the product of derivative b, whatever is the variable. And when you have a definite integral, the way that I recommend doing a U substitution problem is to figure out what the limits will be in terms of U, and then rewrite the problem as I have over here, using U and the new limits. So if U is to be x cubed plus 9, then when x is 0, you put 0 there, and the U would be 9. So that becomes your new bottom limit when you've written in terms of U. And when x is 3, you put 3 here, and you have 27 and 9, which is 36, which would be your new upper limit. And then if you notice the what we have, here I had 9x squared, which was the y value for the curve times the radius. What I did is I factored the 9, 3 times 3, and put one of the 3's out in front to make the 6 pi and left the other one in. Now the reason I did that, to leave the 3x squared right there, is that if this is U, the 3x squared dx is the du. So what I have now is exactly du on top and U under the square root sign. So you have to do a U substitution in a problem of this sort when you have 2 terms that are under a radical sign. And so now I have a constant, number limits appropriate to the new variable, and the single letter under the radical sign, so I can write this as u to the minus 1/2. Well, we know how to do an integral u to the minus half du when it's a single letter, and this is the differential with that same letter. Single letter with an exponent, you add 1 to the exponent and divide by the new exponent. Unless the exponent is minus 1, and in that case, then what you get is the logarithm. U to the minus 1 du is log u. Otherwise, from Math 170, you add a 1 to get plus 1/2, and then you divide by the new exponent. So invert and multiply here, and you get 12 pi square root u, 36 minus square root of 9. Okay, that's 6 and that's 3, so you get 36 pi. So this thing works out very nicely as a u substitution problem. Well, I imagine that we could say all's ashore that's going ashore this morning, so let's do this before I forget. If you were here 16, where we have a curve on the right, x equal y squared, so that's a sideways opening parabola. The line y equals minus x, which is the same as x equal minus y. So that goes like this, and this would be a 45-degree angle in here. And we're asked to get the volume of the figure formed by taking the area up above the origin. So this area, you notice these curves also enclose an area down here, but the problem specifically says it's this one. And so if you think of this area being rotated around the x-axis, we're getting the volume of that geometric figure. So we're looking at shells that would be horizontal, and so right minus left would be your length when the slices are horizontal. So y squared right hand x minus left hand x. So you get y squared plus y, and your radius then would be y from the x-axis, and your thickness would be dy. So your differential volume is 2 pi times your radius times the length of the shell, dy, thickness of the paper. So multiply these together and you have y times y squared plus y. So y cubed plus y squared. And then you see you do your integral by adding 1 to your exponent and dividing by your new exponent. And you put in your limits, y is 0 up to 2, and work out your numbers to the 40 pi over 3, which is what they say it is. So let's look a little bit more at the maple that goes with the disc and the shell method. So if you brought up the package that's Student Calculus 1, notice Maple is very, very picky, as computers are, of course. And so if you want it to work, you have to do just like I have it. So the student has a capital S, and the Calculus 1, you notice, has a capital C, and there is no space between the S in calculus and the 1 there. I can remember at one time trying to get that to work, and I had a space there and it wouldn't do it. It's very annoying sometimes, but anyway. If you end with a colon, any Maple command either has to end with a colon or with a semicolon. If you end it with a colon, then the computer responds to the command, but it doesn't display. It just simply is there. If you end with a semicolon, then it displays, and what you get with the semicolon then is it lists all these different choices that you have in that package. And you see there's a great deal that you could get it to do. Most of which we won't do anything with, but I just wanted you to see how powerful that program is. Anyway, if you type volume of revolution with due regard to a capital V, you notice, and a capital O, and a capital R, and then square root X, SQRT is square root of whatever, 0 to 2, output equals integral. What you're doing is taking the square root curve from 0 to 2 and rotating it around the x-axis. And if you do this, if you think of it as a disk method, for example, your radius is the square root, so your radius squared is square root squared, which is x. Pi times squared radius is the area of your disk, and times dx is the volume. So the integral that's number 2 there is actually a disk method then, a solution to it. And then same thing again, volume of revolution, output equals plot. You see the picture of the surface, the outer surface. Volume of revolution, output equals integral. Now this next one, you notice, is square root x square root 2. So that's a figure, you see, that's in between the two curves. You have square root x and from 0 to 2, and then square root 2 is a line. So that one is the picture that you see if you turn the page. If you want to see what that one is, turn the page, and you see in the green you have the cylinder centered on the x-axis, for which you have radius equal to square root 2, and then the inner one, which is in red, is the same figure that is on the first page, although all that you see is the end of it toward the origin. So as you see, it says up above the picture on the back of the sheet of paper, the volume of revolution around the horizontal axis between square root x and square root 2. So you can see then that it'll give you the integral, it'll give you the actual answer, volume of revolution, if you don't say output equals anything. It'll give you what the volume is. Output equals plot, then, is what draws the graph for you. And then the next, going down the page on the back side of the first sheet of paper, this time the axis is vertical. The formula number 5, volume of revolution square root x. See, before the axis was horizontal, but if you want to go around the y-axis, you type axis as vertical, and you have your integral. And this one was a shell method. If you look at number 5 and think about it, you have 2 pi times your radius, which is x, times your curve, which is square root x. And that's how you're getting 2 pi x to the 3 halves. X times x to the 1/2, you see. So that's actually a shell method integral. And then if you just want the volume, it's number 6 is telling you that. Then this next one, the volume of revolution around the vertical axis of x to the 1/2 power, the square root. So you have the square root for your top curve, and the bottom is your x-axis. So you can, if you like things like this, then I can recommend the Maple program to you, and you can play games with it. This is not, Maple is not anything that is required. But what I will do is I'll give you Maple handouts so you can see what a program of this sort can do. And I leave it up to you whether you want to get involved with it or not. Meanwhile, let's go over and talk about differentials a little bit. So you should not be surprised that here comes another handout. So, first of all, what we want to do is talk a little bit about the idea of what the differential is, because we keep using the term in calculus, and it's easy to take calculus and end up saying, well, that's some mysterious thing I never understood. So I'm trying to address that anyway. There's a little bit of history here first. I mentioned a few minutes ago that Leibniz in Germany and Sir Isaac Newton in England are the co-inventors of calculus. They came up with the equivalent methods at essentially the same time, and so far as anybody knows, they did not actually correspond with each other about it. It's not fair to accuse either one of them of stealing from the other, I think they just both came to the same general ideas at essentially the same time, although their methods are, at least their terminology is somewhat different. So Euler and the Bernoulli family, there were several people named Bernoulli. Euler and the Bernoullis were Swiss, and Leibniz was German, and Euler and the Bernoullis followed the Leibniz ideas, and they talk about what we call a differential quotient. Sir Isaac did not himself at first use the differential idea, and the way that the derivative is presented in the first the Thomas book is more the Newton idea, the limit f of x plus h minus f of x over h as h goes to 0. So here's how you reconcile these things. Say you have a curve and a tangent line. TL is tangent line. I actually defined it over there. It touches the curve somewhere and comes on down to the x-axis. So the t here is your angle of inclination of this tangent line. And you see this and this line are parallel. And so if you have parallel lines, then they intersect the same straight line, then the corresponding angles are equal. So by geometry, if this is t, that is. Okay, so that's geometry so far, not calculus. Okay, so Sir Isaac's derivative as a limit is giving you the slope of the tangent line, which is the tangent, like in trig, TAN, of the angle of inclination. Now, if you start at a point up here, the point where the tangent line touches the curve, and you draw a horizontal parallel to the x-axis, then you have two kinds of differentials in x and in y. So the dx in green is your differential in x, and it's the same number whether you use a d or whether you use the frequent delta. Whether it's dx or delta x, when you're going horizontally, it's the same. From x, say, to a point over here, x plus dx or x plus delta x, either name you like. So these people would have used delta x and dx interchangeably for the differential change in x from this position to someone over here. However, the change in y, the delta y, and the differential change in y are generally different. You can see that they're different in my picture. The differential in y measures the distance from the horizontal at the point where you're starting to study your problem up to the tangent line, and the delta y is the distance from the horizontal to the curve. So if your curve is concave down like this, the delta y is a bigger number than the dy. If it were bent the other way, the dy would, the tangent would be above the curve, and the dy would be bigger than the delta y. The only time they're equal is if your curve is a line graph, so then the tangent is the same as the curve, or at a point where the tangent happens to cross the curve. But most of the time, the delta y and dy are different, but the dx and delta x are the same. They're just the distance from where you started to some point where you're looking at the changes in the function. And so I've written that down over here. So then your delta y, which is the change in the actual function value, is your function value at this point, whether you wrote x plus dx or x plus delta x wouldn't matter. That number is the same as that number, minus your height to your curve back here. So your delta y is here up to there minus here up to there. Whereas the dy is the rise in this right triangle, where the rise is the blue, the run is the green, and the third side is along the tangent line. So here's the little differential triangle, as it's called. Notice that was my title. This is repeated out over here. So Newton's approach to the derivative would be, we use the prime mark for the derivative, thinking of Newton's approach in books now. Newton originally didn't use this mark, he used a dot. Remember, he was either writing with a pencil or a quill pen, so he could stab the paper. A French mathematician named Lagrange is actually who introduced using the little prime mark, but it's clearer what you mean if you use this. With a dot, well, is it really a dot or is it just a flaw in the paper? And so anyway, this is what you learn in chapter 2, I guess it is, in the Thomas book, which you see. So that gives you the slope of the tangent line, and it gives you the tangent of this angle. And you either call it f prime or y prime. Now, because of similar triangles, this is the same angle. And then if you look in this differential triangle, the tangent, the same trig function, that's your slope, is also this side over that side, rise over run, opposite over adjacent, right? And so the derivative, which is your limit, and your differential quotient are always numerically equal. So your limit is your f prime, is your tangent down here, is your tangent up here, that's why I repeated it, is your differential quotient. And Leibniz and the Bernoullis and Euler all use the differential quotient. So you could look at it as a little bit like money.
Hold on to that for you.
You'll help me, right? Okay. So here is 100, okay, with a picture of Franklin. Here are 250s, pictures of Grant. Now you can all see that logically there's a difference, right? You can tell this from that, right? But they'll both buy the same 50 gallons of gasoline. Truck stop down there, $1.99.9. Either way, you get this and that. If you've got an RV or a drum or something to buy 50 gallons. It's amazing, isn't it, that you can buy that much gas. So anyway, the point is that you can have things that are logically different but equal numbers. Okay? Well, that's what your differential quotient and your derivative are. They're always equal, but there is a logical difference in what they are. But you can use them interchangeably. The thing is, this is a quotient, so you can separate it as a fraction. And you can write then that dy is f prime times dx, which we will be doing in chapter 7 and chapter 9 when we work with differential equations. The reason a differential equation is any equation where the unknown is the derivative of some function. So they could just as well have been called derivative equations. But the people that first worked with them were Euler and the Bernoullis, and they were differential quotient people, so that's why they call them differential equations. Little heads up on the Math 333 class. Okay, so finally, back to section 6.3 and arc length. What I wanted to do was introduce the idea today, and then next Thursday we'll go on with arc length. So arc length is the tape measure length along a curve. So if you have a curve again, then the actual length of arc as you go from a point to the point over here would be the delta S in purple. We're thinking of S as arc length. You start out from some place and you have a perfectly flexible tape measure, like the kind people use for sewing or something, that you can bend to fit the curve and stretch tightly. Okay, so from somewhere to somewhere else, your arc length would be increasing, and you call that delta S. Starting here, you could also draw a differential triangle, just like this one, and go dx horizontally, dy up to the tangent line, and then the hypotenuse would be the differential in arc length. You can see that the red and the purple are not exactly the same, but the red is a reasonable approximation, and if delta S is the true change in arc length, as x goes from here to here, and ds is the differential change, then the differential is approximately the truth. Could be more, could be less, depending on how the curve bends. Then dx again is the differential change in x, and dy is the differential change in y. So the limit of the difference between the true change, delta S, and the differential change would be 0 as the differentials in x and y go to 0. In other words, you come back this way with smaller and smaller values for dx, and when you're back about to here, say you cut this down like this, so with the little black triangle that I've just drawn, you could hardly tell the difference between the length on the slant and the purple that's up above. That's what I mean by saying this. So what that allows us to do is get a formula for the differential change in arc length, thinking of arc length as a function either of x or of y as we choose. Because with right triangle trig, we know that ds squared, the hypotenuse, would be the sum of the squares of the two sides of our right triangle, our differential triangle. So you could solve for ds by taking the square root, and then if you think of arc length as a function of x, your differential quotient, ds divided by dx, would be this law of Pythagoras expression divided by dx. And then dx squared over dx squared is 1, and dy squared over dx squared is dy dx squared. Again, our differential quotient equals our derivative, so you can write it that way, s prime, where you're thinking of arc length as a function of x. The derivative is the square root of 1 plus the squared derivative of the function with x. And in the same way, if you thought of x as a function of y, you could also say that your differential quotient is s prime of y, again, numerically equal when you say is, and you get the square root of 1 plus g prime of y, 1 squared, when x is g of y. So we use either this formula or this one in the 6.3 problems. So I wanted to finish today by just doing problem 1, and then what we'll do next Thursday is probably you'll see this much repeated. We'll go on from there and talk about arc length and about surface area. So looking at problem 1, we are told that y is this curve, 1/3 x squared plus 2 to the 3/2 power. And we're working on arc length, which would be the tape measure length along the curve as x goes 0 to 3. So your curve looks approximately like this. You notice when x is 0, 2 to the 3/2 power is your square root of 8, and 1/3 the square root of 8 is a little bit less than 1, because the square root of 9 is 3, and 1/3 of 9, then 1/3 of 3 rather would be 1. So without having an exact number, I know my curve comes into the y-axis below 1 a little bit. And you see if you're at 3, you have 9, you have 11 to the 3/2 power, and it works out, if you take a calculator to it, to be about almost 12. So your graph is basically like this, and you're talking what's the tape measure length along there. So then, according to formula, the derivative of arc length, when you have your function variable with x, would be 1 plus the squared derivative, take the square root. And then what you hope is it's a problem where you can do that integration to get your length. And again, the Thomas book has been out enough years that the problems all work. So, the derivative. Repeat your 1/3, bring your 3/2 down, subtract 1, you get 1/2. Chain rule, because this isn't just x, you see, it's a variable function with x, so times by the derivative of what's inside, which is the 2x. And you notice the 3's cancel, and this 2 cancels that. So it is a problem that'll work in the sense that you can do it by hand. So what it leaves you is this x and this under the square root sign. So then the square, you see your arc length formula wants 1 plus the squared derivative. So square your derivative, you get x squared, and the square of the square root. And if you multiply that out, you get x fourth plus 2x squared. And then it's 1 plus that from the formula. So you see this has been very carefully designed so that the three terms you get under the square root sign are a perfect square. This is 1 plus x squared, quantity squared. That's what you want to look for in the homework in next week in 6.3 and 6.4. And so the square root of this perfect square is the absolute value. Remember, square root of a square is the absolute value of whatever it is that you were squaring. However, x squared plus 1 is always greater than or equal to 1, so therefore the absolute value is just x squared plus 1. So what you have now is the derivative of arc length is x squared plus 1, so the arc length is the integral with the limits on your problem. So you see it's a pretty easy integral. So you finally get 12 as your tape measure length along here. 12 what? Well, whatever's the unit on the tape measure, centimeters or whatever it would be. And so I guess that's probably as much of this you want to hear for this week. Be sure and give me the sign-up sheets. And I will see you Thursday. Rain, shine, or snow. I'll be here, unless they close Micron up.
I think you're getting all three each day.
You may. Oh, in Idaho, you just wait 5 minutes and the weather will change. Yes, thank you.